All right, gang, we're going to go through, we're going to talk about graphs of functions today. So we're in lesson 3. And we're being told here, graphs are one of the most powerful ways of visualizing a function's rule. We can quickly read inputs and outputs. We can also see things like minimums and maximums, and actually the plural of minimum is minima, and the plural of maximum is maxima. But looking at highest points and lowest points, which is basically what this is talking about. All right, just as a quick review, it says here's our function defined by the graph below. That means that this curve is our function called f of x. So sometimes we put a little f next to it. It says find the value of each of the following. And we remember from last week, that number in the parentheses, that's our input, and we're looking for the output. So if the x is 4, 1, 2, 3, 4, I go over to 4 and I look up, and there's the point on that function, so the output would be 1. F of negative 1 means I'm going to look over in the x direction, negative 1, and then look up, and where am I? I believe I am at 6, so the output would be 6. Okay, so it's reading an input and an output, and we talked about that last week. Next question, for what values of x does f of x equal negative 2? And I talked about this last week. We kind of draw that little horizontal line through negative 2, and we see where that curve crosses negative 2. And it crosses negative 2 when x is 1 and when x is 3. Okay, so this answer has this question has two answers. It says illustrate on the graph, and what it means by that is draw that little horizontal line. The next question says state the minimum and maximum values of the function. That's exactly what it sounds like. The minimum means what's the lowest point it hits, and the maximum is what's the highest point it hits. The minimum it reaches, when we're talking about outputs, it goes down, 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 till the y is negative 4. So the minimum would be negative 4. It happens to hit negative 4 when x is 2, but it's not really asking about the x there, it's just asking about the y. Now, how about the maximum value? Well, we see the maximum value. This is kind of a weird question. Let me erase my writing here. The maximum value should be the highest point that the function reaches. Now, most functions, we put a little arrow at the end to indicate it goes on forever. And if that's the case, we would say it has no maximum. But this one actually doesn't have an arrow at the end. So the highest point it reaches on both sides here would be 6. So we would say the max would be 6. The maximum value is 6. Now, in the first question, they had the graph drawn for us, and the second question, they don't. But we can make the graph here. What we need to do is produce some outputs. So they've given us an algebraic definition for this function. They're saying that g of x is equal to 2 times whatever the x is, and then we're going to add 3. So in this table, I'm just going to do those computations. I'm going to save a little time and hit pause here. I'll do those computations, and then we're going to plot those points on the graph. So just as a reminder to what I'm doing, I'm just substituting in that x value into this 2x plus 3, and I'm going to get the outputs. So I've written down all those computations. Why don't you hit pause and then do your arithmetic, see if your numbers match mine. And there are my answers. So remember what we just produced. We produced the output for our input of x. So I'm going to plot each of these points on the graph. The input was negative 3. The output was negative 3. The input was negative 2. The output was negative 1. And I'm going to put those points on the graph. Okay, so that was our question B, draw a graph. So hit pause, put those points on, see if your answer matches mine. And this is what happens with this function. It turned out to be a nice line. Now, the question is, should I connect the dots or not? I don't know. Maybe sometimes we do, sometimes we don't. We could connect them and it makes a nice line like that. Or we could just leave those points there. It depends on the context of the situation. Let's go to the next page. Now in this question, we've got the same idea. We're going to do the computation. We have a table here. The difference here is that we have an x squared. So let's see what this looks like. And the point here is that the idea is to translate between an equation and a graph. All we have to do is plot inputs and outputs, right? We just plug in, find the outputs, and then we can graph them to see what this function looks like. So let's see, if I put in negative 3, I want to remember negative 3 squared means negative 3 times itself. Negative times negative would be a positive 9. Okay, so fill out that table and then graph it. Check to see if yours matches mine. So when I graph this one didn't come out a line, this one came out a nice curve. We actually call, anytime we have an x squared, we call that a parabola. A quadratic function is the name of that, okay? And it comes out to be a nice smooth curve. I did sketch them, I connected the dots and I drew arrows at the end. Kind of, again, depends on the context whether we do that or not, okay? But yours should look like mine. All right, now we get into the heavy lifting of this lesson. This is where it gets a little bit weird. In fact, the guy who made this lesson even said sometimes the function rules get all sorts of funny and can include being what's called piecewise defined. Piecewise means, we talked about this in class last week, there's pieces of it. These functions have different rules for different values of x. These separate rules combine to make a larger and more complicated rule. And let's see if we can figure out what this looks like. All right. So here is our function in number 4, exercise 4. Our function, look what they did here. They broke it into pieces. Guess what? That's why we call it a piecewise function. This function has one rule when x is less than 0, and it has another rule when x is greater than or equal to 0. That's really strange. Well, what that means is the graph's going to look a little bit different over each of those sections. So here's what I'm going to do. I'm going to go into the table. And this function breaks at 0. So what I'm going to do is I'm going to draw a line right before 0. So we're going to look at all values when x is less than 0, and then values when x is more than 0 or equal to 0. So when x is less than 0, our calculation is, let's do 2x plus 6. So when x is -3, I'll do 2 times -3 plus 6. And I got that right up here. And then when x is -2, I'll do 2 times -2, and I'll add 6. And then 2 times -1, and I'll add 6. And then I'm going to stop because it tells us when x is 0, now we're going to change the rule. So let me calculate those, and I'm going to plot them on the graph. So here's what those 3 points look like when x is less than 0. So our function looks like this, and I could connect those. When x is less than 0, if I kept going backwards in the negative direction, it would look like that. But the problem is, right at 0, it changes. The rule changes. So what I'm going to do is, when I hit 0, I'm going to put a little open circle right there, because I don't know exactly where it is when it's 0. It gets really, really close to a certain number, but it's not there because it's less than 0. So now our function changes. Now our function becomes, for anything more than 0, our function becomes 6 minus x. So our rule down here is to take 6 and then subtract x from it. So I'll do those calculations as well. 6 minus that x, 6 minus this x, 6 minus this x, 6 minus this x, and I'm going to do those calculations and plot those points as well. So here's my second part of this graph. Up to 0, the graph looks like this, but after 0, the graph looks like this. So it's going in a different direction. It's kind of slanted a little less than the first part was slanted. We call that its slope. So it changed in the middle, it changed at 0. We're not going to do too much with piecewise functions, but I do want you to know what they look like. They're kind of this f of x here, this idea of f of x, and then we break it down into different pieces. We use this little squiggly bracket to say it's this to here, and then it's this to here. Okay? I missed a question here, question A. Evaluate each of the following. So if I look back at the function, let me erase that. When x is 4, well, I have to figure out which piece of the graph I'm in. When x is 4, 4 is more than 0, so I'm going to use this part of the graph, or this part of the function. F of 4 would be 6 minus 4, would be 2. When x is -3, -3 would be this part of the function, so I would do that calculation, 2 times -3 plus the 6, and I actually already did that down here, it's 0. Okay, so that's called a piecewise function. Don't worry about them too much. I want you to have seen what that looks like. All right, so that's our lesson for today. You're going to work on the homework questions. So as you work through these fluency questions, we're using the graph to answer. One of the questions here is, what is the y-intercept? That means, where does it go through the y-axis? Okay, so read through those questions. Here's a table to fill out and graph. And then on the next page, we're reading this piecewise function and interpreting it. It's about text messages and cost. And then down at the bottom, do your best. They've given you this piecewise function. Do your best on it. I don't expect perfection. But in this case, the dividing point is at 1. So I'm going to go, it's less than 1 or equal to 1. So I'm going to draw a line here. And you're going to do one calculation for less than or equal to 1 and one calculation for more than 1. Okay? See what that looks like. Do your best. Put a big circle around any you don't understand, and we'll talk about them when we see you next time. Okay? Bye-bye.